So we know there's two types of waves, there's transverse and longitudinal waves, but we actually need more words to be able to compare these waves to each other. So we're going to look at how we can do that now. We can represent waves on a displacement distance graph like this. So here, a displacement of 0 means that's where all the particles are when there's no waves, when they're all at rest. We say they're in equilibrium. Okay, but when there is a wave, they get displaced, they get moved up or down. So displacement is the distance and direction of each particle, if the wave is made out of particles, from the equilibrium position. The most important displacement is the amplitude. The amplitude is a maximum displacement from the equilibrium line. So in this example, it's 15, okay, 15 meters. Another important feature is the wavelength. Wavelength is the distance between a point on a wave and the exact same point on the next wave. So for example, from peak to peak, or trough to trough, which is the bottom to the bottom basically. Or we can measure it from here to here, or even here to here. So one of the easiest ways to actually measure it is measuring across multiple waves. So if I measure from the peak on the left all the way to peak on the right, that's two whole waves, okay? And that distance is approximately, I'd say 7.6 meters. So if I do 7.6 meters divided by 2, because there's two waves there, that gives me the wavelength of 3.8 meters. Okay, example number 1. The graph shows the height of water waves at the beach. Determine the amplitude and wavelength of the waves shown. Okay, let's start with amplitude. So on the y-axis here, we don't actually have displacement of the wave. We have the height of the wave. So let's mark out the top and the bottom. So at the very top, we have 8 centimeters height, and the bottom we have 2 centimeters height. So to get the amplitude, we need to figure out the maximum displacement from the equilibrium. So what I would recommend doing here is doing 18 minus 2. That gives me 16 centimeters from the top to the bottom, and then divide that by 2 to get the distance or the displacement from the equilibrium, because that's 8 centimeters. So if I mark it like this, from the equilibrium line to the very top, it's going to be 8 centimeters. Okay, now for the wavelength. So I'd say in this case, the easiest way to measure the wavelength is just measure from the bottom of the peak to the bottom of the next peak here, because that's very close to axis. I can just read off it. So there's 1.6 on the left and 4.0. So 4.0 minus 1.6, and that's in meters. So the wavelength is 2.4 meters. Okay, example 2. Now we've got more waves, and again we're asked to calculate the amplitude and the wavelength. And the amplitude for this one is pretty straightforward because we've got the displacement and it's already been aligned with the graph there. So I would say the amplitude there is 0.42. However, you need to read the y-axis very carefully. It does say time 10 to the minus 6 meters. So I need to make sure I include that in my amplitude. Now for the wavelength. Now this one's a bit more tricky because it's a bit, the waves are quite closely packed to each other. So I would recommend measuring more than one wave. I would measure across multiple waves. So let's start with 1, 2, 3, 4, and actually 4.5 waves. So the distance of 4.5 waves is 0.8 meters. So if I take 0.8 meters and divide by 4.5, that gives me the length of one wave. That's 0.1777 recurring, or approximately 0.18, and that's in meters. Okay, third and final example, the diagram shows the particles in a longitudinal wave. Determine the wavelength. So you need to recall the definition of wavelength. It's the distance from one point to the exact same point on the next wave. So all I do is find one point on this wave and find the exact same point on the next one. So for example, from where the particles are quite compressed together, that's called a compression. And all the way to the other one, the next one along it. So the distance there is from 0.8 to 2.0. So I just have to subtract those distances, and that gives me the distance between those 2 points, which is 1.2 meters, the length of one wave.